Okay, we might get started with our next talk. So next up, we have Gregory Saunders. He has a PhD in computer science and has been working in the financial industry for more than 12 years. He found that he had data and he had time, and he loves random forests. So welcome.
Thank you. Yes, well, as Rob said, I work in the financial services industry, and I had a pile of data about ASX equities, and I had some computing horsepower and some free time. So I decided to see what I could do with random forests. And of course, being in financial services industry with data about equities, what do we want to do? We want to predict how they're going to perform in the future. So we'll see if we can get anywhere along that front later on. So a quick introduction to supervised learning. So random forests are used for, obviously, supervised learning. There are two types of supervised learning, classification and regression. In classification, you're given some data and it's already been classified, right? So you're given several data points, usually thousands of data points, tens of thousands, millions, and you've got the classifications of those data points already, okay? And what you want to do is you want to predict the class of unseen data. In a regression problem, the desired result is not a class, but a number, usually a real number, right? So it's like predicting the result of a function. You're given a set of samples, again with known results, and you want to predict the results on previously unseen data. And I'll be focusing on regression in my presentation. So what does the data look like? This is what the data looks like, very simply. You have a matrix of training data over here with rows for each sample of data and columns for each feature. And given that this is the training data, we know the results of this data. So we have the vector of results here. Now, notice that the matrix of training data and the results are real numbers. Okay, so if you have data that isn't a real number, for example, it's a string, you're going to need to convert it to a real number. You can convert it to an integer, of course, because that's a real number. Now, that's the training data. That's how we're going to train our supervised learning model. But we're going to test it with some data where we don't already have the results. And again, it just looks the same as the training data. It's a matrix with one row per sample and one column per feature. Now, in my sample data, the features are just measurements about stocks on the Australian Stock Exchange. So it could be analyst estimates of future earnings. It could be price momentum, all the kinds of things you can look up on Wikipedia. It's all pretty standard stuff, but I can't actually tell you how it's derived because that would be proprietary. So before we go and talk about random forest, let's just have a look at my data. So if I move over here, so can never type when I'm in front of everyone. So here's my training data. As you can see, just a matrix of real numbers. And if I print my training results, that's just a vector of numbers, and we'll note a little problem here. We've got some nans in our data. That means those results are missing. We'll get to that in a second. And if I just have a look at my test data, there's my test data, also a matrix. Can everyone read that, by the way? Yeah. Yep, good. Okay, so let's go back to the presentation. So why use random forests? There are a number of supervised learning algorithms available, many of them in the Scikit-learn package. So why pick random forests? Why not use something like neural nets? They're sexy, they're hot, everyone seems to love them. But I've gone with random forest, and the reason I went with random forest is because they have some advantages. They're a bit easier to use than other learning algorithms because they have few tuning parameters, right? So with any supervised learning method, you have to give it some parameters about how it's going to perform its work, and different parameters will produce different results. So with fewer tuning parameters, there's fewer different values to choose, and that makes it simpler to implement. Nevertheless, despite the fact that there are few tuning parameters, it still produces good performance. Also, you don't need to standardize your training data. With certain other supervised learning algorithms, that matrix of training data, real numbers, you have to standardize it, which means you have to convert it so it has a mean of 0 and a standard deviation of 1, right? You don't have to do that with random forests, so that's good. It has built-in cross-validation, which I'll talk a little bit more about later. And it automatically quantifies the importance of each of the features for you. So it has some nice advantages. So move on here. So what are random forests? Well, random forest is an ensemble learning method. What the hell does that mean? In computer science, we like to use normal words like ensemble with bizarre meanings so that we look smart, right? In fact, all that it means is that we're taking two or more other learning methods and aggregating their results. That's all that ensemble learning means, right? And in this case, the two or more other learning methods are decision trees, right? Decision trees, take two or more of them, you've got a forest. Okay. So what are decision trees? Here's one. This one is actually built from my data. Excuse me. So what it's basically saying up here is that if feature number 75 is less than 0.0292, then take this branch. Otherwise, take this branch, right? And you keep doing that all the way until you get to a leaf. Here's a leaf, right? And once you get to that leaf, you've got a value, and that's going to be the value that it outputs, okay? Now, the real tree is something on the order of 40 levels deep at its maximum, but I've only obviously printed out 3 levels here. How are decision trees constructed? Well, you give them the training data, and basically what they want to do is try to choose the feature where you can split on values of that feature and derive the most information, or split the data into categories that give you the most information on each side. So it just builds it up iteratively like that until it gets to a leaf, which is a leaf will have one or more samples, each of which have the same value in them. Now, in a regression problem, of course, the values are real numbers, so most leaves are likely to have just one sample in them. In a classification problem, a leaf would have multiple samples, all of which have the same class. So, what's good about decision trees and what's bad? Well, they have low bias, high variance, and they're prone to overfitting. What on earth does that mean? Well, this little diagram, I'm indebted to UBS for this diagram. It basically illustrates the difference between bias and variance. So over here we have bias. You can see that if we were shooting at this target, we've obviously missed, but we're missing the same all the time, okay? So we've got a little bit of bias up in this direction, but it's clustered around this point. With variance, we don't have so much bias here, but we do have a large amount of variance. There's a great deal more difference between the data points than there is over here. So that's the difference between bias and variance. So the idea with random forests is that we're going to build a bunch of decision trees, and we're going to try to reduce this variance whilst hopefully not affecting the bias too much. Okay? So how do we build a random forest? Well, you would imagine that it has the word random in it somewhere. And this is how it's done. It's called random sampling with replacement. If this is our training data here, where we've got sample 1, 2, 3, 4, and 5, right? What we do is we take a random sample with replacement. Now, with replacement just means that we can take the same sample more than once, okay? So here we've got sample 3 more than once, sample 5 more than once, sample 1 only once, okay? And then what we're going to do with this random sample is we're going to train a decision tree on that, okay? And then the next step is to take another random sample which presumably, unless we're very unlucky, will be different from the first one, and we're going to train another tree on that. And we're going to keep doing that until we've trained the desired number of trees. Now, the idea is, firstly let me say that the method that this uses is called bagging. That will come back later. And as I said, it reduces the variance without increasing the bias. Okay? So we're going to build a forest of decision trees, each of which is built with a random sample of the data. So it's not going to use all of the data. It's going to use some of the data, but it's going to get some of that data more than once. Okay, so I mentioned earlier the tuning parameters. What are the tuning parameters if we're building a random forest? Well, there's three, but really it's only the first two that get a lot of action. Basically, the number of trees, the number of features to consider at each split, and the depth of the tree. So let's look at those in detail. The number of trees, right. So more trees is better, okay? But you suffer from diminishing returns. So once you get above a critical number of trees, the extra predictive power of the model doesn't improve very much more, okay? And typically you're looking at a few hundred to a few thousand trees, sometimes tens of thousands, depending on the size of the data set that you're looking at. Of course, the more trees, the slower it is to construct the model, okay? So you want to strike a balance between the number of trees and how long it takes to construct the model. The second tuning parameter is the number of features. So remember that the columns of the training data represent the features of the training data. So in my data set, that was things like analyst estimates of forward earnings, price momentum, and those sorts of things. So we don't just choose a random sample of, a random sample of the samples. We also choose a random set of features that we're going to allow the model to split on at each point when it's building the trees. And because we're using different data and different features to build each tree, you end up with a whole bunch of trees that are hopefully not highly correlated with each other. Okay? Now, if you use more features, of course, it's going to choose the same feature every time because it's choosing the feature that gives it the best information split at each point. So if all the features are available at every node on every decision tree, it's always going to choose the same one. So if you cut that down, you increase the bias, but you reduce the correlation of the trees. Okay? And we want trees that aren't too highly correlated, because if they're highly correlated, then really we've just got a decision tree. The third tuning parameter is the depth of the trees. How deep do you make them? If you go too deep, you risk overfitting the data. Okay? Remember that the leaves of the tree in a regression problem contain typically only one sample and therefore one value. Okay? So if you get to that leaf in the tree, you're always going to get the same value. If you cut the depth of the tree somehow, you're going to get multiple samples, and the value that you're going to get as a result is the average of the values for those samples. Okay? So you're generalizing, whereas if you don't cut the depth of the trees, you're potentially overfitting. Now, just by creating a forest of decision trees, we mitigate this risk of overfitting, but we don't eliminate it entirely. So forests are better than decision trees in that aspect, but they're not, they don't fix this problem completely. One of the problems with limiting the depth of the trees is that we have no way of knowing ahead of time how deep the trees are going to be. I told you earlier that the tree I showed you was approximately 40 levels deep, but the only way I could know that was to actually build the model, get the tree, and ask how deep is it, right? So we don't know ahead of time how deep the trees are going to be. So limiting the depth of the trees can be a little bit of a problem in determining how deep they should go. Okay, so let's have a look at Scikit-learn's random forests. How do we install Scikit-learn? Just in case you haven't done this yet, it's pretty simple. You're going to need NumPy and SciPy, and then you just pip install Scikit-learn. If you're not a fan of pip, then you can download it from scikit-learn.org. That's enough of that. So, before we can use the random forest model, we need to deal with that missing sample data. Remember I showed you a minute ago we had some nans in our data? Well, we need to deal with that. So let me show you how we can deal with that. Scikit-learn has in it tools for doing what's called imputation. And in random forests, you typically use the median for missing values. So if you imagine a feature, you've got some missing values for that feature. What you do is you calculate the median value for the feature, and then every missing value, you just replace that missing value with the median. And the reason why you want to do it that way, remember, is because a decision tree splits on a certain value, and if it's less than the value, it's going to go left. If it's greater than the value, it's going to go right. So if you pick the median for the missing values, you're just picking the middle value, right? So it's not going to bias it one way or the other with respect to that feature, okay? And in the imputation code, the missing values are by default represented by nan, but you can configure that. So if we just have a look at the code that you could use to do this, that's it. Just import the imputer, then create an imputer with a median strategy, fit it to your sample data, and then transform your sample data with the fitted model, and that will replace any missing values with their medians. Now, you have to do the same thing to the test data, right? If you don't do it to the test data, of course, you'll have problems when you try to predict the result. So you do the same thing using the same imputer for the test data, because remember, the model is built using the median of the training data, not the median of the test data. So if I'll just cut to a demo of this. So where am I? Okay. So if I just have a look for any missing data here. This is just some NumPy magic to tell me if there's any missing data. So, okay, so what this is telling me is that basically for each column of data, so for each feature, are there any nans in that data? And where it's true, yes, there are nans, okay? Nan is not a number, if you're not familiar with that term. Okay, so how do we deal with it? Here's our code. Let that run. Okay, so there's the code that I used earlier, and here is the result. It's replaced all of the nans with their medians, and now there is no column which has any nans in it. Okay? And of course, we're going to have to do that for our test data as well. Where are you, mouse? So let's just do that for our test data. Yeah, it's really hard working like this. Okay, now, if you recall, we also had the problem that there was some missing data in our results. Okay? So what I'll do is I'll just use this, which is pretty much doing what the imputer did, to replace the nans in the results with their medians as well. Okay, so now we've cleaned up our data. Let's go back to our presentation. Okay, so that was using the imputer to clean up our data. But what happens if a feature is missing entirely? You've got nans in every row for a certain column. Okay, now one way to deal with that, of course, would be to just delete that column. I didn't want to do it that way because I was repeatedly constructing training data over a period of time, and it would happen that in certain periods of time that certain features were missing, and in other periods of time they were present. So what I decided to do was just replace that feature with all zeros. Okay, if it's all zeros, then there's no differentiation between any sample on that feature, and it will never be chosen by a decision tree as a splitting variable. So we can just replace them all with 0 using code like that. Okay, we just create a mask where if all of a certain column is nan, then just put 0 in there. Okay? Okay, and don't forget to check the training results too. Okay. All right, so how do we actually construct our learning model? Here's the code. Not terribly hard to do. So we import the random forest regressor. We create a random forest regressor instance, and I'll tell you about the parameters in a second, but once we've created it, we fit it to our training data, and then we predict the result of our test data. That's all that it takes. So what are these parameters to the random forest regressor? N estimators is the number of trees. Right? Max features, that's the number of features to consider at each split. These are the default values for the parameters, by the way. Auto, just in a regression case, means all features. In the classification, a supervised learning case, it's the square root of the number of features. The maximum depth is none, so we could set this to some level as the maximum depth if we had an idea about what maximum depth to choose. And then these 4 parameters here are actually just a different way of constraining the depth of the tree. Remember I said earlier that you can't know ahead of time how deep the tree is going to be. So instead of specifying a maximum depth, what we could do is we could say there must be a certain number of samples left in order to split on a certain node in a decision tree, right? So the default value of 2 means that if there is even only 2 samples, we can do a split and create two leaves. Whereas if you set the minimum samples to, say, 3, then if you had only 2 left, it would just leave that node as a leaf and average its results. Okay? So that's a way of constraining the depth by limiting how many samples there has to be when it does a split. Another way of doing it is to say, well, any leaf must have at least this many samples. That would be another way of constraining the depth of the decision trees. Another way would be to say, well, there has to be a certain weight of samples. If there are 1,000 samples and you want 10% of them in each leaf, then obviously you 0.1 for the minimum weight, and there would have to be at least 100 samples in each leaf. So again, constraining the depth. And then another way to do it is to set the maximum number of leaf nodes. So basically you're constraining the depth by saying there cannot be more than this many leaves. And then the last parameter here, n jobs, that basically is just an optimization. If by default it will use 1 CPU core. If you set this to -1, it will use all available cores on your machine. Or you could set it to an integer, which is some number of cores that you want it to use. And basically it just means that it will do it faster. So let's cut to a quick demo. Just clear the screen there. So here's my code. So I'm only going to set the number of estimators here. I'm going to leave the max features at auto, and I'm going to use all available CPU cores. Okay, now that's actually, it's training at the moment. So unfortunately my laptop is only a dual core machine. So we have to wait a little bit. Obviously, if you've got a machine with a lot of cores and really fast clock speed, that would be better. Waiting, still waiting. There we go. Okay. What happened to our predicted results? Oh yes. There they are. Okay, so that's our predicted results. Okay, so we have some results. We've predicted the performance of some stocks. So the question is our prediction any good? That's the subject of my next slide. Is the prediction any good? Okay, how can we evaluate the results? Well, the default way of evaluating the results when you're doing a regression is the coefficient of determination, or the R squared value. Now, interestingly enough, this value can be negative. And that's kind of weird, because if it's R squared, right, how can R squared be negative? And the answer is that it's not calculated as the square of some value. The way that it's calculated is basically using the ratio of the squares of the differences between the correct result and the predicted result over the squares of the differences between the correct result and just the average of all the correct results. Okay? Now, in my data set, the results are standardized, which means they have a mean of 0 and a standard deviation of 1, which means that if the result is negative for me, just predicting 0 for everything would be a better predictor of the results than using my model. So let's take a look and see how it goes. So the way we can see the score is we can use the score method on the model to have a look at it. Oh dear, how embarrassment. My score, my R squared scored, is negative 0.02. Doesn't look like my model has done very well. It would have been better, actually, to just predict 0 as the performance for all stocks. Well, what can we do about this? Well, actually, it turns out in predicting stock performance that R squareds below 0 aren't all that uncommon. So those of you who have superannuation in the stock market, take note. So what can we do that gives us a better result? Let's go back to my slides here. Well, that doesn't give us a better result, but that helps us to evaluate our results a bit differently. Well, in finance, we often use what's called the rank correlation as a way of evaluating the results. So how can we do rank correlation in SciPy or in Scikit-learn? Well, we're using SciPy. The Kendall-Tau and the Spearman-Rowe are two different measures of rank correlation. So we can use this code to measure the rank correlation of our results. So let's take a look at that. Okay, so here we have our results. The Kendall-Tau result was basically 11%, and the Spearman-Rowe was 15%. Now, actually, in finance, those numbers aren't too bad. I mean, they're not great, but they're not too bad. So we could actually try out this model and see if it actually works in a simulated portfolio. And the results that I got, basically in 2014, it outperformed the model we were really using to run our customers' money. But in 2013, it significantly underperformed. So still a bit of work to do here, but it can work. There you go. That's a different way of evaluating the results of our regressor. And I've got to play again. Here we go. Okay. Now, I mentioned earlier cross-validation. What's cross-validation? So the idea of cross-validation is that you, instead of training the model, on your entire training set of data, you train it on part of the training set of data, and then you use the rest of the training set to test how effective it is, okay? To test how good it is. And one use for doing that sort of thing is to optimize the tuning parameters. What you can do is you can try a certain set of tuning parameters, say 100 trees and a max features of 0.5, and see how good it is. And then you could try another set of tuning parameters, 150 trees and max features of 0.4, and see how good it was. And then you can use that to optimize your tuning parameters. And Scikit-learn has tools to help you to do this. The problem is it kind of takes a while, a bit slow. I have to write some extra code. Don't really want to do that because I'm lazy. So how can we do that? How can we get sort of something like the same result without doing all that work? Out-of-bag estimates. So remember I told you earlier that the process of taking those random samples with replacement that are used to train the decision trees is called bagging. Okay? Well, if you've got a random sample with replacement that's the same size or smaller than the original set of samples, then you're going to, in all likelihood, have some samples that miss out, that aren't in the training data that are used for any given tree. And if you're training 100 trees, chances are, well, the more trees that you train, the chances are higher that for every single sample in your training data, there will be at least one tree where that sample was not in the training data for that tree. Does everyone follow me there? For every single sample, there will be at least some trees that sample wasn't used in the training data for that tree. So what do? We take those trees that this sample was not used in those trees, and we use them to predict a result for that sample, and then we do that for every sample, and as long as you've got enough trees, then the chances are you'll be able to get a result for every single sample, and then you'll be able to measure the result for that sample, and that gives you an estimate of how well your random forest is performing, and then you can use that to optimize your tuning parameters. Now, is it as good as doing proper cross-validation? No. Is it faster and easier? Yes. So let's go with that until we determine that we need to do the whole hog. Okay, so that's out-of-bag estimates. And how could we use that to optimize our parameters? Well, here's some code to do it. I've got just a list here of the different values for our parameters. So we'll try 100 and 200 trees. And we'll try 0.3, 0.4, and 0.5 value percentages of the number of features to use at each split. And then what we basically do is we just take the product of those different parameters and then train a regressor with each of the values, each of the combinations of the values, and we can use this OOB score, out-of-bag score, to estimate the performance of the model, and we just remember the one with the best score. Okay? And that gives us a quick and dirty way of optimizing our tuning parameters. All right, nearly done. So I mentioned earlier as well that we can get a quantification of the importance of each feature out of the model. How do we do that? Well, the way that you determine how important a feature is basically where it appears in the tree. If it's up near the top, it's more important because more samples will go through that tree, that node. But if it's down near a leaf, it's less important because fewer samples will go through that node. You can basically quantify the importance of each feature in each tree and then average them across all trees to get the importance of the features in your model. So just take a quick look at that. If I just, all I need to do is go s.feature importances, and there's the importances of all of my features. So these are, incidentally, these numbers all sum to 1, right? So it's the relative importance is measured there. Anyway, so that basically tells you that this feature here is sort of 2% of samples on average. This one here is 1.3. This one here is very few. So it gives you an understanding of how important each particular feature is to your model. Okay, and then really quickly, because I'm probably going over time. How do we get to the individual trees? The estimator has an attribute called estimators, which you can use to get at the individual trees. And then Scikit-learn has an export graphviz method, which will allow you to dump a tree out into graphviz file format. And then you can use graphviz tools to produce something like that. that you can use to visualize each of your trees. Now, you're probably going to have hundreds, maybe thousands of trees, so how useful this is, I don't know, but there you go, you can do it. All right, I'm nearly done. So if you like random forests and you like Scikit-learn and you didn't like my talk now, there's some other talks about them that you can go to later today and on Sunday. So at 1:10 p.m., Chris Hausler is doing a talk on an end-to-end machine learning ecosystem in a quarter. And our esteemed host, Robert, will be doing a talk later this afternoon on predicting sports winners using data analytics with Pandas and Scikit-learn. I believe Random Forest will be making an appearance in that talk as well. And then on Sunday, we've got a bit of a tutorial on doing data science in Python, which should be pretty awesome. Okay, that's it. I'm done.